Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 15, 2026, exactly 1 week ago. It introduces a new training paradigm that embeds an explicit reflection loop into the learning process, achieving performance gains of up to 81% in complex multi-step environments. The paper is titled Experiential Reinforcement Learning, and as we'll see later, the implications for making agents more sample efficient are quite significant. Figure 1 illustrates the evolution of learning paradigms. On the left, direct learning simply imitates fixed examples. The middle panel shows reinforcement learning with verifiable rewards, where the agent learns from scalar feedback but must implicitly figure out what went wrong. Finally, on the right, experiential reinforcement learning introduces a new loop. Here, the agent explicitly generates self-reflections on its actions and then internalizes those insights to update its policy directly. While Figure 1 outlined the theory, Figure 2 makes the comparison concrete using a navigation task where an agent acts without prior knowledge. The top panel depicts standard reinforcement learning with verifiable rewards, where the agent relies on trial and error driven by simple success or failure signals. Because this feedback is sparse, the model often repeats mistakes in a back-and-forth cycle without grasping the underlying rules. In contrast, the bottom panel illustrates experiential reinforcement learning. Here, the agent pauses to generate a verbal self-reflection, like realizing this block is a wall, which helps it internalize the lesson and permanently correct its behavior. Alright, moving from the concept to the architecture, Figure 3 diagrams the full experiential reinforcement learning pipeline. It starts in the top left with a first attempt, where the policy generates an answer and receives environmental feedback. Then the middle panel shows the key innovation. The model uses that feedback to generate a verbal self-reflection, which guides a second attempt on the right. Finally, the bottom section illustrates internalization, where successful second attempts are distilled back into the base policy, so the model learns to succeed without needing the extra reflection step. So, with the pipeline established, Figure 5 presents the final evaluation rewards across 3 environments: Frozen Lake, Hot Pot QA, and Sokoban. The green bars represent experiential reinforcement learning, while the blue bars show the standard baseline. The most dramatic difference appears on the right in the Sokoban task. Here, the QN model jumps from a near-zero score of 0.06 up to 0.87. This massive gain likely occurs because Sokoban requires long-horizon planning, which benefits heavily from the reflection loop. Meanwhile, the other panels show that Frozen Lake and Hot Pot QA also see consistent improvements, confirming that the method generalizes well. Okay, while the previous figures showed the final scores, Figure 4 charts the full learning trajectory. These 6 plots track validation reward against training hours. Notice how the green curves, representing experiential reinforcement learning, consistently climb much steeper and earlier than the blue baselines. This difference is starkest in the Sokoban panels on the right. There, the standard method flatlines near zero, but the experiential approach achieves rapid gains, proving that the extra compute used for reflection actually shortens the total training time needed to solve complex tasks. So, having seen the trajectories, Table 1 breaks down exactly what drives those gains. It lists the final rewards for both models, but crucially adds 2 ablation columns on the right to isolate the impact of different components. The far right column, labeled ERL without reflection, shows the most significant drops. For instance, removing the reflection step causes the QN model score on Frozen Lake to plummet from 0.94 down to 0.60. In Sokoban, the drop is similarly severe, confirming that the structured reflection loop, and not just the memory buffer, is the primary engine behind these results. Wrapping up the big picture is that explicit self-reflection acts as a bridge between raw trial and error and durable learning. By internalizing these insights, experiential reinforcement learning produces agents that can solve hard planning tasks without incurring extra inference costs. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.